Okay, hello. In this video, I will discuss a question from MJ11, paper 41. This is an electric field question. So let's go. Define electric potential at a point. So I think by this point in time, hopefully you have done enough examples to know that the definition for A2 are fairly standard. So maybe you can take a while to recall it. This is normally defined as work done in bringing a unit positive test charge from infinity to a point in the electric field. Alright, so generally candidates will struggle to get full marks if they didn't mention bringing a unit positive charge. So this part here, work done in bringing a unit or work done per unit charge, this is 1 mark. So if you recall in your AS, whenever there is potential, potential difference, or when the unit is volt, this is joule per coulomb. And in AS, many people would define potential difference or EMF wrongly because they forget that it is work done per unit charge. So the 1 mark is a unit positive test charge, including the word positive. So for you to gain this mark, I need per unit or a unit, and I need the positive test charge. And of course, the remaining mark will be work done in bringing a charge from infinity to a point. This would be the 2nd mark. Alright, so it might seem very straightforward and standard, but please make sure you define it properly because we are quite strict about this. Alright, part 2. Well, in this question, you have 2 small spherical charge particles, P and Q, that may be assumed to be point charges, okay, which is the general assumption for us when it comes to sphere. So you can go and watch the lecture video if you're not sure why we can do so, but we assume that all the charge are concentrated at a single point, not distributed along the surface of the sphere. So you got 2 charges here, okay? Particles are in vacuum. Particle P is fixed in position. Particle Q is moved along the line joining the 2 charges as illustrated in figure 4.1. So what this tells us is this particle Q, okay, this one I'm going to color over it. So this particle Q, we will travel or we will drag it along the line here. So this Q will go along from here to here. So of course you can see your X will decrease until maybe 0. But it won't be 0 lah, because weird things happen when 2 charges are at the same place. Alright, so the variation with separation of the electric potential energy, so this is electric potential energy, of particle Q is shown. Okay, so number 1. You will notice that whenever you are given a graph, the first thing I would suggest that you do is circle, highlight, you can't highlight in the actual exam, so maybe circle with a pencil the prefix and the units, because sometimes careless mistakes can happen, like you've forgotten the prefix or you've forgotten the units. Alright. The second thing is to ask yourself, does this graph make sense? Okay, so you can see here, right, as Q approaches P, so let us just sketch out the position of P and Q on this graph. So P is fixed in position. So P, okay, I don't know the charge of P, so I'm just going to draw. So P is here, it is fixed in position. Whereas charge Q, okay, is the one that is being dragged on in this direction. And X is the separation between P and Q. So you can see the first thing is that when Q approaches P, this potential energy seem to decrease, or is it increase? Well, it depends on whether you understand the idea of this negative or not lah. Okay, so just a sidebar, whenever your energy is negative like this, potential energy negative, what does this tell you? It tells us about who is doing the work. Is it the particle that's doing the work, or is it the field of P that is doing the work? So think about it this way. Whenever the potential energy is negative, it means that, let's say, for example, you travel from, I don't know lah, let's say I take a point like 12 to 6. you can see that your potential energy is actually decreasing, right? You're going from a smaller negative number magnitude to a larger magnitude negative number. So your EP is decreasing. Okay, that means at infinity your EP is 0. Meaning when Q is very, very, very far away, EP is 0. So that's why the entire EP is negative. You might actually recall that whenever EP decreases, it means that something else is doing the work. Meaning you can naturally travel in this direction. Can. Because your potential energy is decreasing. So if you struggle with this concept, right, you could always think about gravity, because you and I exist in gravity, and gravity is a bit easier to think about. Let's say you have a floor like so, and then you have a ball like so, and let's say the ball decreases its potential energy. So let's say from point A to point B, the ball drops here, so you can see EP decrease. Now if your potential energy decreases, it means that work is done by the potential field. In this case, gravitational field. Because the force that is pulling the ball down is our good old familiar mg, or weight. Gravitational force. Okay? So in this case, similarly, if the electric potential energy decrease, we can then conclude that there is work done by the electric field. Specifically by the electric field of P lah. Actually P and Q lah, but P. And this means that P and Q attracts. So these are information that you can gain from the graph. I mean, not just by looking at the values, but also seeing that the potential energy decreases as P and Q are closer. Okay, just like if you look at the green color drawing, you can see the gravitational potential energy also decreases when A is brought closer to the ground. So similarly, A would sort of be your Q, the moving mass, and this ground or surface of Earth will be your P, which is the mass that is not moving, obviously. Okay, so when you travel closer to the mass, your potential decrease, meaning work is done by gravitational field, because when the field does the work, its potential decreases. Okay, so when it's work done by the gravitational field and your potential decreases, you do work ma, your energy decrease. Gravitational field do work, gravitational potential energy will decrease. So this is very obviously attractive. Just like similarly in this case, if we look here, when Q approaches P, the potential energy decrease. So work is done by the electric field. So P and Q attract. Okay, because the electric field does the work, that's why the potential energy decrease. A second hint to show you why it attracts, right, is because this potential energy is always negative. So if this potential energy is always negative, this means that there is this negative tells you there's work done by the electric field. Okay, or 0 and then to negative, which is very similar to gravitational field. So this means it is attractive. So you might be able to immediately tell, or if you are still starting off your journey with electric field, you might want to just see the parallel with gravitational field. All right, so we're gonna carry on. Part 1, state how the magnitude of the electric field strength, so electric field strength is represented by the alphabet E, is related to potential gradient. Now potential gradient is dV dr. So as I've mentioned before in the lecture video, this one is like some past year favorite. So electric field strength is negative potential gradient. You might be wondering, do I need to write this in full sentences? Negative potential gradient. Well, the answer to that is, it depends. If you write equation, then you should tell us what E represents, what dV dr represents. Which means you also have to write the whole sentence anyway. The only thing you don't have to write is the word is. So it is shorter to actually write in the sentence. Okay, so a note here, if using equation, define the terms. Why? Because the question didn't define. So you have to then define what the question did not define. Alright, so use your answer in 1. Show that the force on particle Q, is proportional to the gradient in the curve. Alright, so let's think about what we want to prove. The question is asking us to prove force is proportional to the gradient of the curve, which is dV dr. So we're going to start off with what we already know. So part 1 normally is like a hint lah. You know E is dV dr, so we can start from here. Okay, can? So we'll start from E is equal to dV dr. And we try to figure, negative dV dr. And we try to figure out what can be done so that we can actually come up with force inside this equation. So the first thing I'll do is I'll multiply both sides by Q. Multiply Q. Okay, so you're going to have QE here, and you're going to have Q dV dr, which, by the way, I will omit the negative sign because we just want the proportionality or the magnitude. Okay, just like in the mark scheme, if you don't include the negative here, it's okay. But you must say that the electric field strength is the potential gradient. So I'm just going to put this in a bracket, showing that it's optional. But the accurate one is including of a negative. Alright, so we're going to continue. This will be force, right? This QE is F1. So I'm just going to write this one as F. And this Q is constant. Right? This one, constant. So Q is constant, and hence you have F is equal to a constant multiplied by dV dr. So F is proportional to dV dr. But it's 2 marks, and they gave you lines. This means you have to explain all the important steps. I think the first important step I want to talk about is F being proportional or equal to QE for the same charge. So I'm going to write that as a sentence first. Say the force on Q is proportional to the electric field strength. If you define electric field strength here, so here's how I can write a bit less, comma E. So force on Q is proportional to E. Then if you feel like it, you can write F is equal to QE. Okay, then you can say since E is also proportional to the gradient, potential gradient, we need another one because this one is the same statement as this. So of course you won't get 2 marks for the same statement in 2 different parts of the same question. Alright, so I think the second thing we need to look at is what on earth is the gradient of the curve in this one. So let's go back. Gradient of the curve is actually dx of the potential energy. Hiya, you need to relate potential energy to potential. So this is not the end. We still need to relate to potential energy. So again, if you are very lost, this is electric PE, and this one is electric potential. Is there an equation that relates electric PE and electric potential? Alright, so if you were thinking that your electric potential and your electric potential energy can be related, basically V and EP, this is also QV. Okay, so this is your second important relationship. Potential energy is proportional to electric potential. Okay, so and the reason why that is if you, let's say I summarize everything for you lah. Show F is proportional to gradient of the graph. Let's revisit the graph. The graph is potential energy against distance. So it will be F is proportional to D dx EP. Okay? And at the same time, you know F is equal to QE. And also at the same time, okay lah, let me make this a bit faster. Potential energy is QV. Right, so force is QE and potential energy EP is QV, because remember they asked you to define electric potential, so that was work done per unit charge. Okay, so to find electric potential energy, you will take electric potential times the unit charge that you divided previously. Okay, so from here you can tell that the important relationship is here to here. So this is 1 mark. Important relationship is here to here, so this is 1 mark, and don't forget to relate back to this one. Alright, okay, so the first mark already written, force is proportional to electric field strength. Second mark here, electric potential energy is proportional to potential difference, and hence since E is proportional to dV dx, because you see I can take out the Q there, right? So the Q are the same, this is the same charge Q, so you have E is proportional to dV dx. So we're going to start from the bottom and relate back to here, because they are asking you to show this. So you're going to start from this and arrive here. Alright, so this is step 1, or rather step 0. And then you multiply both sides by Q, and then you notice QE is force. Okay, so multiply both sides by Q. How do you know you want to multiply both sides by Q? Either by experience, or you start from what you wanted to prove and try to see if you can work your way backwards. Alright, so when we multiply both sides by Q, you will notice that its force is proportional to electric field strength, because charge is constant. And electric potential energy happens to be QV. So electric potential energy also proportional to V. So this is your 1 mark here. I'm just going to write M and 1 mark here. Alright, so we're going to complete the explanation now. Number 1, the force on Q is proportional or directly proportional to the electric field strength. Number 2, since E, the electric field strength, is also proportional to potential gradient, and potential V is proportional to EP, your potential energy, hence force is proportional to your gradient of the figure 4.2. Okay, so again, 1 mark is you understanding that you have to state force is proportional to E. This is the first mark. Second mark is when you say that V is proportional to EP. And since EP and E, this one and this one, sorry, this one and this one is related, and this one is the gradient of the graph. So by like 4 degrees of separation, this gradient is proportional to force. Okay, so you need to outline the 4 degrees of separation. First degree of separation, force is proportional to E. Second degree of separation, E is the gradient of V. Since V is also proportional to EP, so force will be equal to the gradient of EP. Alright, so that's 4 degrees of separation. So this kind of question can be quite hard if you've never encountered them before. So we're gonna move on. Second part, magnitude of the charge on each of the particles P and Q is this much. Okay, calculate the separation of the particles at the point where Q has an electric potential energy of negative 5.1 eV. So this is a bonus question, I think maybe because it tortured you up there already. Recall that potential energy is QV, alright, and you will also know that to find electric potential, you can use KQ over R square. Wait, no square, my bad. KQ over R. You will also notice that there's a negative here. So since we are looking for the absolute magnitude, I can choose to not substitute the negative sign. Being aware that this is E volt, so I will multiply this by the electronic charge to convert to joule. So we always have to convert to joule whenever we use the equations in this format. Why? Well, because you have a physical constant K, and your final answer is in meter. So every other units here have to be in SI. So we know the value of K. K here is 8.99 times 10 to the power of 9. You have the value of Q, which is 1.6 times 10 to the power of negative 19 squared, because you got 1Q, 2Q. Divide by the distance. So you're looking for the separation R or X. Alright, so I think I noticed one thing, which is this and this can cancel off one of them, and then I am left to find the value of R. Okay, so to find the value of R, I'm going to press my calculator now. Right, so that will give me 2.8 times 10 to the power negative 10. Wow, miss this one 4 mark leh. Well, this is an old question from 2011, so don't expect that many marks lah. Maybe 3 next time. So conversion of E volt from here to here is 1 mark. So if you convert your E volt correctly, is 1 mark. You use KQQ over R, you get 1 mark. Okay. Substitution or other substitution is 1 mark. Final answer is 1 mark. Okay. So this one is pretty easy. If it comes out, then good lah. Alright. So by reference to the graph, state and explain. So you need to give a statement and provide an explanation whether the charge have the same or opposite sign. So hopefully you've watched enough examples and understand that if let's say they are attractive, which I spent some time explaining why they are attractive, the two charges will have the opposite sign. But I guess you need to explain it a bit more. So you could say that the potential energy is decreasing as X decreases. Okay, when P and Q are brought closer together. So hence, work is done by the electric field. So if the electric field is doing the work, the electric field is attracting the charges. Alright. The effect in any on the shape of the graph for doubling the change on particle P. Okay, so if you make P double the charge, so you can look at your calculation here. If let's say my P become double, so let me highlight P a different color. So let's say this is the charge for P. So if you multiply this Q by 2, it just means that your energy will also multiply by 2. You can see they're proportional. Okay, so you could say that the energy will double. So the energy or EP will be double or 2 times. Okay, because from potential energy is K, Q, Q. They are the same Q over R. Now your potential energy will be K, 2Q, Q over R. So this new potential energy is twice the old potential energy. Alright, so if all the values become twice, so let's think about the graph a bit. Now all these values are going to double. So let's say, for example, 1 will become 2, 2 will become 4, 4 will become 8. So the graph becomes steeper. All right, so you can say that the shape of the graph, the gradient of the graph will increase because they want the shape of the graph. So when you describe shape, it's either it will keep the same shape or it doesn't keep the same shape, it will be reflected. So all of these terms are used to describe changes in graph. But in this case, it's pretty straightforward. You could say that the gradient of EP increases, not double, just increases. Okay, increase by how much need to calculate. Alright, increases, or you could say that the graph in figure 4.2 is steeper. Alright, so I think that's all for this question. Some standard explanation, bonus calculation, and here is where the tricky part is. So I guess this is the hardest it can be, where they ask you to try to relate. Basically, they are testing the 4 pillars and whether you know their relationship or not. So if you know, right, it will be pretty straightforward. If you don't know, then, if you know, you can stop the video now. But if you don't know, I would just like to reiterate or explain to you. You have F, you have electric field strength, you have electric potential energy, sometimes it's U, depends on the question. You have electric potential V. So electric force, electric field strength, electric potential, energy, electric potential. So these 4 things are correlated. There's a relationship between all these 4. And you have to know, for example, here to here, E is equal to F per unit charge. Same way, if you go down, V is equal to potential energy per unit charge. That's why we say F and E is directly proportional. And V and EP directly proportional. Of course, if you go back up, you multiply lah, okay? So this is from definition. If you travel upwards, and these are all in your notes. So normally when you revise, you could always just draw this really quick square diagram just to remind yourself lah, what are the relationships between these things. Work done is equal to QV. Alright. Second thing is the left and right relationship. So from force, if we want to get the potential energy, we will integrate FdR. Okay, and then if you travel back, you actually dV dr. But inside the video, if you remember, there's a negative sign here lah. Okay, so this means potential energy is equal to this and V is equal to this. Why is there a negative? If you care about the reason, go watch the video. Okay, if you don't care, just accept that the negative is there, depending on your brainwave. Alright, but the connectors are important. Like for example, in this question, they ask you to show that this is proportional to the gradient of this. Proportional, the gradient of this. And they can choose anywhere they want lah, inside this multi-arrow relationship. So if you're familiar with this, you can slowly work your way back. Okay, so we started off with this one. Potential is equal to, sorry, not potential. What am I drawing? Electric field strength. There we go. Now it's fixed. Is potential gradient. And then we work our way backwards, because this is what they asked us to do in part 1. Alright, so hopefully that's helpful. Thanks for watching. Recommend and like our videos. Don't forget to subscribe, and I will see you in the next one. Take care now.